All right, so we're going to do discussion 7-1, chemical equilibrium, which is the last discussion in Unit 6 and 7 for SL. All right, so dynamic equilibrium. So a lot of reactions don't go to completion. These reactions are considered reversible reactions. So reactants can combine together to form products, and products can combine together to form reactants, and the reaction can go both directions. So a lot of reactions do not go to completion. One that I'm performing right now in my house is burning wood in my fire. We can't take ashes and turn them back into wood. So that would be an example of a reaction that goes to completion. Another would be if a solid is formed and precipitates out of a solution. If a solid is formed and it's no longer reacting with a solution, and so that reaction will go to completion, as well as when a gas is formed and escapes from a reaction situation or a solution. The gas leaves the scene, it's not going to do any more reacting, so that would be a reaction that goes to completion. But in a closed system, we can reach a state of equilibrium. And equilibrium is a state at which the concentrations of reactants and products remain constant, and the rate of the forward and reverse reactions will be equal to each other. Dynamic equilibrium just means that the forward and reverse reactions are happening, they're ongoing, but there's still no change in the amount of the reactants or products or the rates of the reaction. Think about it like running up an escalator that's moving down. The escalator is moving, you're moving, but there is no apparent change in your position because you are moving up at the same rate that the escalator is moving down. So we can look at equilibrium graphically. The first graph we have here is the rate of the reaction over time. Now at the beginning of the reaction, all we have are reactants. We have not yet combined the reactants, so we do not have any products. Once we combine our reactants, the rate of reaction begins to slow down for the forward reaction because the reactant particles are being used up to make products, and so there are fewer of them available to collide. At the same time, the rate of the reverse reaction is increasing as product particles are produced because they are then, once they're produced, are able to collide into each other and react to form reactants. Now, both reaction rates will continue to change until they steady out and become equal. Equilibrium is established when the rate of the forward and reverse reactions are equal to each other. Now, if we look at the amount of reactant and product over time, again we see at the beginning of the reaction we have all reactants and no products. Once the reaction proceeds, reactants begin to be used up and products begin to be formed. Once we get to the point where the concentrations of reactants and products remain constant, that is when we are at equilibrium. So the equilibrium concentrations of reactants or products will never actually go to zero, but it'll steady out at some level. All right, so equilibrium constant expressions are mathematical expressions that we use to assign a number to a particular equilibrium. And that number will tell us the relative amounts of reactants and products at equilibrium. So here we have a generic reaction, reactants A plus B, and an equilibrium with reactants C plus D. And we see J, K, L, and M are just the stoichiometric coefficients on the reactants and products. So the equilibrium constant expression is the concentration of products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. So for this particular reaction, C and D are our products. So we have the concentration of C raised to the Lth power times the concentration of D raised to the Mth power divided by the concentration of A raised to the J power, and so forth. Now, K sub C is what denotes the equilibrium constant, and it's different for every single reaction. It will remain constant for any reaction at a particular temperature. If we actually change the temperature, we'll actually change the value of K sub C. And it's important to know that changing the temperature is the only thing that will change the value of K sub C for a particular reaction. If you change the pressure or the concentration, nothing will happen to the value of K sub C. So take a moment and pause the video, pause the video and practice this. I ask you to write an equilibrium constant expression for the following balanced chemical equation, which is the combustion of propane. So go ahead and do that, and I'll be back in a second. delicious. Okay, so K sub C will be the concentration of carbon dioxide raised to the third power times the concentration of water raised to the fourth power divided by the concentration of propane raised to the first power, because there's a coefficient of 1, times the concentration of oxygen raised to the fifth. And we consider this a homogeneous equilibrium because all the reactants and products are in the same state of matter. So it's important to note that we do not consider solids and liquids in equilibrium constant expressions because solids and liquids don't really have concentrations. We can change the concentration of a gas by compressing the gas and forcing all the gas particles to be in a smaller volume closer together. And we can change the concentration of an aqueous solution either by removing solvent or increasing the amount of solute. So we only consider aqueous and gases. So take a moment and write this equilibrium constant expression, noting that water is in the liquid state in this expression. All right, so the equilibrium expression will be the concentration of the ammonium ions times the concentration of hydroxide ions divided by the concentration of ammonia. Note that there is nothing raised to any power here because all the stoichiometric coefficients are 1. Now this is an example of a heterogeneous equilibrium in which we have reactants and products all in different phases. We see that the reactant side has gaseous ammonia and liquid water, and on the product side we have aqueous ammonium and hydroxide ions. All right, so we can also calculate the quantity or the actual value of K if we're given equilibrium concentrations. So this problem says nitrogen dioxide decomposes at high temperatures according to the following equation. And there it is. It says calculate the equilibrium constant if the equilibrium concentration are as follows. So it gives us the concentration of the reactants and the products. So all we have to do to solve this is write the expression for K sub C, plug in the numbers in the appropriate expression, and solve, and you will get the equilibrium constant expression. All right, so take a moment and give this one a try. It says the equilibrium equation for the oxidation of sulfur dioxide is as follows. And there it is. Calculate the equilibrium constant if the equilibrium concentrations are as follows. And there are the concentrations. So pause the video, take a moment and work this one out. Okay, so the equilibrium expression, K sub C, is the concentration of sulfur trioxide squared divided by the concentration of oxygen times the concentration of sulfur dioxide squared. And when you plug in the values, you get an equilibrium constant expression of 14. All right, so we can use equilibrium constants to determine how far a reaction will proceed and in which direction the reaction will be favored. So if K is much greater than 1, then the reaction will favor the formation of products. The reaction will go nearly to completion. If K is much smaller than 1, then the reaction will favor the reactants, and the reactants will hardly proceed. Now we have to think about this mathematically. If we go back to the previous slide, if we look at the equilibrium constant expression for this equilibrium we have here, if K is going to be a very large value, much greater than 1, then that tells us that the numerator, the concentration of sulfur trioxide, must be much greater than the combination of the concentrations of the reactants. If the value for K was very small, then the denominator would need to be much bigger than the numerator, which means we would need to have a lot more reactants than we do products at equilibrium. All right, we can actually also predict the direction a reaction will have to proceed in order to establish equilibrium by looking at something we call the reaction quotient. The reaction quotient is denoted with a capital Q. Now, when we write the expression for the reaction quotient, it's the same exact expression as the K expression, the equilibrium expression, but we're not sure if the concentrations given to us are equilibrium concentrations. So the first thing we'll do is solve for Q and compare the results to K. If Q is equal to K, then that means the system is at equilibrium because those concentrations produced are equilibrium value for K. If Q is much greater than K, then the reaction will have to shift left in order to compensate, or to establish equilibrium, I guess you could say. And if Q is much less than K, then the reaction will have to shift toward the product side to establish equilibrium. So here's an example. It says we have 0.5 moles, 0.1 moles of O2, and 0.7 moles of sulfur trioxide. They're introduced simultaneously into a 1 liter vessel at 1000 Kelvin. Gives us the equilibrium equation and tells us that the value of K at 1000 Kelvin is 2.8 times 10 to the second, or 280. So, first thing we have to do is determine if the mixture is at equilibrium. So, we'll solve for Q and compare it to K. So when we solve for Q, we get the value of Q to be 19.6. So, is this at equilibrium? Well, 19.6 is not the same number as 280, and so it is not at equilibrium. So the question now is, which direction will the reaction need to proceed to establish equilibrium? Well, equilibrium has a K value of 280. Now 280 is a much bigger value than 19.6. So if we want to increase that number for Q, then we have to increase the amount of products that form. We have to make that numerator in the expression larger. So that means the equilibrium will have to proceed toward products to form, since Q is less than K. All right, so we can change the value of K sub C if we change certain things about the equation. So here we have an equation with gaseous hydrogen combining with iodine to form gaseous hydrogen iodide, and the K value is 100. So if we reverse that reaction, what will happen is we'll take the square root, or excuse me, if we reverse the reaction, we'll take the inverse of the K value. And that makes a lot of sense, because if we reverse the reaction, the reactants become products and the products become reactants, and we just flip-flop the numerator and the denominator in our K expression. So the new K expression would be 1 times 10 to the negative 2, the inverse. If we have the coefficients, we'll take the square root of the K value, so it would become 10. And if we double the coefficients, we'll square the coefficients, so 100 will become 10,000. Now, I haven't really seen this come up yet, but it is part of the curriculum, so it's probably something you should know. All right, Le Chatelier's principle. Le Chatelier's principle says that if a stress is applied to a system at equilibrium, the equilibrium will shift so as to minimize the effect of the change and reestablish equilibrium. So what I want you guys to do now is actually pause this video and go to that link at the bottom of the page and watch a short video on how Le Chatelier's principle works, and then I'll come back and explain it. If you have access to this file on Blackboard, you can just click the link there, or you can just copy it into the search bar in your internet browser. Alright, so there's 4 things we can do to cause a shift in the equilibrium. We can add more reactant or add more product. We can remove a product or reactant as it's formed. We can change the pressure on a gaseous system, or we can change the temperature on a system. So if we have reaction A plus B in a reversible reaction with C plus D, if I add more A, that is going to cause a shift to more products. If we think back to the video that you just watched, if you watched it, removing A shifts the balance toward reactants, and so in order to reestablish equilibrium, more products would need to be made. I like to think about it like a tube of toothpaste. If we squeeze on the A-B side of the tube of toothpaste, then more toothpaste is going to come out, which would be products on the C and D side. I know it's a little bit weird, but it helps. So adding more A will shift the equilibrium toward products. If we add more D, the opposite will happen, and will shift the reaction toward reactants. If we remove C as it is formed, again, we'll be tilting the balance of the equilibrium toward the reactant side, and so more products will need to be made. Now, if we change the pressure, it's important to note that pressure always flows from high pressure to low pressure. Now, the number of moles of gas on each side of the equation will give you the relative partial pressures of each side of the reaction. And the side with more moles of gas will be the high pressure side. So if I increase the pressure on the system, I see that we have 4 moles of gas on the left and 2 moles of gas on the right. So increasing the pressure on the system will cause the pressure to flow from high to low. So it'll flow from the side with more moles of gas to the side with less moles of gas, or to the products. And if we decrease the pressure, the exact opposite will happen, and the reaction will shift to the reactant side. Now if we change the temperature, please remember, changing the temperature will actually change your value of K sub C. But we also have to remember that we have to treat heat as a product or a reactant. And in an exothermic reaction, heat will be a product, and in an endothermic reaction, heat will be a reactant. So in this case, we have an exothermic reaction, so heat is a product. Now if I heat up the reaction, we're adding more product, and we know that if we add more product, it will push the reaction toward the reactant side. So if I cool the reaction, that's like removing a product, and if we remove the product, it'll shift toward the product side. Finally, adding a catalyst will not change the value for the equilibrium constant. It'll have no effect on the position of equilibrium. All it will do is help the system get to equilibrium faster. And that is it for topic 7.1. If you have any questions, please bring them to class, and thank you for watching.